morning, dear students. Today we have a lesson. The name of lesson, Introduction to Finite Element Modeling. Subject, Methods of Analysis and Synthesis of Design Solves. The lecturer is me. I am Danilova Gulmira Tulindiyevna. I am Associate Professor of Department of Information Technologies and Security at Karaganda Technical University. This lesson is intended for students of specialty computer science and software. Today is our first lesson and we begin to learn this material. Okay, let's start. Computational method. Second, the fine element method. Third, mechanical approach. The fourth, the mathematics behind the method. The last, finite element discretization. The finite element method are nowadays one of the most frequently used computational methods in solving scientific and engineering problems. This success is mainly due to the fact that finite element methods are able to reflect the original mathematical model in a very natural way. Let's consider computational methods. With the aid of increasing computational power of microprocessors and parallel and distributed systems, science and engineering is more and more based on computer simulation. Scientists and engineers model reality using mathematics tools and then use computers to compute solutions for the given problem. This process can be summarized in the following picture. You can see on your slide. The first step of the simulation process is visualization. Scientists and engineers spend considerable effort on analyzing the physical systems and trying to discover mathematical relationships that describe its behavior. This most of the time results in ordinary and multiple differential equations. For example, Navier-Stokes equations. The solution of these equations is most of the time impossible to carry out with analytical methods. Therefore, they have to be mapped from a continuous infinite dimensional space into a discrete finite dimensional space. This process is called discretization. And finite element method enters the picture during this stage. Once the continuous model is mapped to its discrete counterpart, the solution of the systems can be found with methods for solving linear systems of equations. The finite element methods were first invented by structural engineers who based themselves on strictly physical basis. However, mathematicians later discovered that finite element methods could be classified as a subset of the Galerkin methods for the solution of PDEC. This way, the method gained a broader mathematical foundation which extended its use to many engineering problems. Nevertheless, this difference in the engineering and mathematics points of the view resulted in two different interpretations, which also affects the way the methods is used in practice. Physical interpretation. The continuous physical model is divided into finite pieces called elements, and laws of nature are applied on generic elements. The result are then recombined to represent the continuum. Mathematical interpretations. The differential equations representing the systems is converted into a variable form and solved by line combination of finite sets of triad function. Finite element notation. As the name suggested, the finite element treat the continuous problems domain as a collection of individual finite elements. The problem parameters are defined on each of the nodes of typical element. Let us now have a look to the key definitions of the finite element methods notation. First, dimensionality. The elements can be defined differently depending on the problem context. Dimensionality indeed expresses whether the elements has 1, 2, or 3 spaces dimensions. Nodal points. Every element is described by its nodal points. Frequently, the nodal points are chosen to be the corners of the elements. However, in case of non-line geometries, nodal points are also defined on the edges. Geometry. This term is used to describe the domain on which finite element discretization needs to be applied. It can be smooth and irregular, for example, rectangle plane, or complex, for example, surface of a machine part. The geometry is defined by the placements of the nodal points. Degrees of freedom. The degree of freedom is the number of ways in which the original problem domain can change its states. In this case of continuous problem domain, the degree of freedom is infinite because problem's characteristics can be defined in each point on the domain. In the discrete finite element methods domain, instead, the DOF is limited by the number elements because problem characteristic can only be defined on the nodal points. Nodal forces. A set of nodal forces or any other actions dependent on the problem are defined on each nodal point. From the mathematical point of view, this corresponds the non-homogeneous right-hand side of the government discrete elements. Let's consider mechanical approach. As hinted in the introductory part of this lecture, there are different approaches to the setup of the finite element methods. In this slide, we will describe in simple mechanical problem aim to derive that discretizes finite element methods equations by using the principle of mechanics of materials. We decided to start discovering finite element methods this way, because most of the terms and conceptions in the mathematical formulation, which we'll treat in the next part, find its original in conceptions of mechanics of materials. Furthermore, understanding the connections between the physical model and the mathematical formulation is very valuable, as it enables us to have big control on the problem treated. Formulations of bar member. In these sections, we will treat a one-dimensional bar member, fixed at one end and free on the other. You can see on the slide. The member is actually loaded by distributed load Q and point and load P. All the parameters shown on the picture are givens except for the actual strain, which is the unknown. The principle of virtual work will be applied for the solution of the problems. Let us start by defining the internal strain energy of the member. Strain energy. The stress-strain relationships in a bar is given by Hooke's law. You can see these equations on your slide. Where equations second is the strain energy density is defined as follows equations. Equations third. To obtain the strain energy, we must integrate the energy density over the whole volume. Furthermore, we can use the definitions we made in the previous slide to obtain the following relationship between the unknown function U and strain energy U. You can see equation. You can note that rigidity is most of the time constant and can be taken out of the integral. However, as we are treating the general case, E and A can be function of X. The external work on the system can be defined in a similar way. External work is defined as force multiply displacement. Therefore, we have to identify the external forces on the systems and integrate their product with the displacement over the whole volume. Two kinds of external forces are acting on the considered system. First, the distributed load Q. Second, the point and load P. The distributed load is continuous and therefore integrable. However, the endpoint load P is singular and it has to be treated with the delta Dirac function. Nevertheless, for our purpose, it can be included in Q, keeping this way the setup of the problem simple. The external work is defined as follows equation. The minimum potential energy principle. Let's consider. for systems to be in equilibrium, internal energy and external energy have to equal each other. However, as we will not be treating the original continuous systems, but the discrete approximations, this equality is unlikely to hold. Instead, we will define the following total potential energy function, which will have to be minimized. You can see the next expressions. According to the principle of variational calculus, a function is minimized when its variation equals to 0. You can see equation. Hrenikov and Mike Henry formulated a 2D structural problems as an assembly of bars and beams. Current used a variational formulation to approximate PDEs by line interpolations over the triangle elements. Turner wrote a seminal paper on how to solve 1- and 2-dimensional problems using structural elements of triangle and rectangle elements of continuum. Now we consider weighted residual methods. The class of differential equations containing also the one-dimensional bar described above are given as follows. The equations first. You can see the border. It follows that the equations 1 multiply this by weight function v and integrate over the whole domain, we obtain the next equations. For the inner product to exist must be square integrable. Therefore, equations second is called variational form. We can replace U and V in the formula with the approximation function. For example, equation first. The function phi and function xi are of our choices and are meant to be suitable to the particular problem. For example, the choice of sine and cosine function satisfy boundary conditions, hence it could be a good choice. Function u is called trial function and function v is called test function, because the differential operator L is second order and consequently function u must be 2 times continuously differentiable. Therefore, we can see function u as an element of finite dimensional subspace on the infinite dimensional function space C. The same way, you can see the function. Now we can replace function U and function V in equations with the approximations U and V to obtain the next. Function R is called the residual and it's always orthogonal to V. This is because the inner product is equal to 0. If we substitute the approximate test function V of equations into equation second and exchange summation and integrate the we obtained, by definition, the above equation should be satisfied for all choices of D. This is only possible in the inner product facies. The next step is finding a suitable test function. One obvious choice would be taking the test function equal the trial function. In this case, the equations would become the next equation. This method was proposed by Galerkin, and therefore it is called Galerkin's method. The last equation is also called the strong form because the test space in this case has more continuity than necessary. As said in the previous section, the solution space of the problem has more continuity than necessary. Furthermore, the strong form is not symmetrical, which is physically contradicting. To resolve the issues, one can integrate the equations by parts to obtain the next equation. You can see on your slide. The last term is equal to 0 because of the boundary condition. This new form of the problem can be rewritten as the next expression. Integrated by parts, we eliminated the second derivatives of u from the problem. This way, we now need less continuity than before. This is why the last expression is called the weak form. A is commonly called strain energy, as it corresponds to the energy stored in mechanical systems due to deformation. The integration, however, also changes the space in which V has to be defined. In fact, now the V is introduced, there is a need for more continuity than just L. For keeping the symmetry, the solution space can be defined as bounded by values of the next equation. As P and Z are necessarily smooth functions, the above requirement can be translated to the following expression. Function obeying the rule belong to the so-called Sobolev space, and they are denoted by H1. We also required V and U to satisfy boundary conditions, so we denote the resulting space as the next equation, reaches the mark. The final form of the problem becomes the next. Finally, substituted again the approximate solutions u and v, we obtain the next variable. More explicitly, substituting u and v, you can remember we chose them to have the same base, and swapping some summatitions and integrals, we get to the final stage with other finite element equations. The finite element equations you can see on your slide, as it can be seen these aligned systems of equations, with the only unknown being c. The equations can be solved using any methods for solving line systems element, and the approximations to the u will be found by constructing function u with the given parameters c. Connection to the physical model. The systems of equations conclude the mathematical derivation of the finite element equations. Let us now turn back and compare the results of our mathematical derivation with the results obtained in the mechanical approach. Strain energy. We had derived in the section 3 the strain energy as the next equation. The mathematical formulation instead produces the next equation. At first sight, the two expressions seem to be different. However, a closer look reveals that they actually lead to the same concept. The first thing to note is that the starting point of the two different analyses is not the same. In fact, for the sake of generality, the mathematical derivation has been carried out with a general differential equations describing many different situations, including the axial strain of a bar. The parameter z, in effect, has no counterpart in the mechanical derivation, as it stands for the internal sources of energy, for example, heat. The parameter P stands for the resistance of the body to deformations, which is translated in mechanical approach by element analysis. Finally, as finite element methods use the Galerkin methods, U and V are chosen from the same space. It is easy to see with the information that the two expressions are equivalent. External work. The two different expressions obtained for the external work are clearly equivalent if V is used instead of U. You see on your slide the weak form. Finally, comparing the weak from equations obtained by the two analyses, we clearly see that they describe the same main principle. It is the variation of internal energy has to be equal to the variation of the external work. On your slide, you see. With this comparison, we conclude the second part of this paper, which was dedicated to the mathematical derivation of the finite element method equations. In the next sections, we will discuss an example, and we will transform the already derived finite element equations into matrix equations. Let's consider finite element discretization. In this slide, we will try to solve an example by using the finite element method. Also, the example is quite simple in nature. It contains many of the fundamental finite element concepts. Let us take the initial value problems with constants, coefficients. Then we divided its domain into n subintervals. Subintervals is called a finite element. The trial function can be chosen arbitrarily as long as they fulfill the requirements of the space in which they are defined. However, it is wise to select a function basis with local support. This means that the function should get the value 1 in the node G and 0 in all other nodes. As we will see this way, we obtain tridiagonal matrices instead of dense matrices, which makes the solution of the problems less computational intensive. A suitable trial basis for these problems is the line head function, defined as the following expression. With the basis in previous slide, we construct our approximate solution. It is interesting to note that the coefficients correspond to the values of function u at the interior nodes. Let us now go back to the weak form derived in previous slide and substitute this trial basis into the equation. The problem at this point can be easy solved using the previous derived Galerkin's method. A little more work is needed to convert these problems into matrix notation. We should consider now a typical finite element and derive the matrix equation for it. Afterwards, we will combine the single elements to obtain the global matrix equations. The approximation function u on a typical element takes the following form. Expression 1. Written in matrix notation, the above equations looks like expression 2. The same can be done also for function v, function xi, the formula requires derivatives of u and v, which can be computed as follows. Matrices. You can see this matrix on your slide. Let's continue. You can see on your slide this equation. The calculations of the integrals is rather complicated. It's therefore worthwhile to divide the formula into smaller, manageable parts by defining the next. Substituting the values into this formula, we obtain the matrix. The matrix K is called element stiffness matrix. In a similar way, one can obtain AM is the next equation. AC is the last equation. You see this formula on your slide. You may analyze this equation. Let's consider the next slide. The matrix M is called element mass matrix. The external work matrix cannot be evaluated for arbitrary function Q. We will therefore use a line interpolant of Q. Q equation you may see on your slide. Using the above approximation, the integral is computed to give where L is called element load vector. Now the task is to assemble the elements into the whole system. In fact, we have to sum each integral over all the elements. For doing so, we can extend the dimension of each element matrix to n and then put the matrix at the appropriate position inside it. With all matrices and vectors having the same dimension, the summation looks like. Doing the same for the mass matrix and for the load vector. Substituting this matrix from the expressions in the next, we obtain the following set of line equations. You look at your slide. This has to be satisfied for all choices of D. Therefore, which means that the expressions in the squared brackets has to vanish. This last matrix equations represents the line system equation which has to be solved in order to get coefficients for the approximate solution U. Here you can see reference concerning these materials. Try to answer the next questions. First, what fine elements do you know? Finite element discretizations. Approximation of an infinite dimensional function. Thank you for your attention.